Welcome back, ladies and gentlemen. We're going to be continuing our exploration of the atom, but now, instead of just looking at the individual bits, the protons, neutrons, and electrons, we're going to take a look at how they're arranged, or at least one idea of how they're arranged. The Bohr model of the atom. You should have seen this last year when you were studying in grade 9. The Bohr model is a way of putting the pieces together that allows us to do a lot of powerful things. Invented by a guy called Bohr. What's the key difference between this and other things? Well, Bohr introduced the idea of energy levels. He put the electrons sort of in shells or orbitals around the nucleus where the protons and neutrons are. Let's take a look here. In your notes, you can see some diagrams. We're going to be drawing a few. We're going to be using them. So we're going to have in the center a nucleus. And that nucleus is going to be filled with protons that are, remember, P positive, and some neutrons that are N neutral. Now, in this particular case, we're going to start off with a simple one. We're going to start off with good old hydrogen. It's got one proton and no neutrons. I think you can see here why it is that I introduced you guys to that notation, right? Where we end up putting things into P positives and N neutrals, or N zeros, because it makes it a lot easier to write all of this. We don't have to write the whole word. No one ever wants to do all the work if we don't need to. Now, this, of course, is the nucleus. This is the center. So we can say that this is the nucleus. And this central core is filled with protons and neutrons. In this case, just protons, because this is going to be good old hydrogen. How do we know? One proton, always hydrogen. Anyway, one proton, of course, has one electron. Now, there's a couple different ways to do it. Usually we just put a dot of some form, but for the purposes of reminding ourselves about all the different notations, I'm going to use E minus. And that E minus is going around in an orbital like so. And this would be the Bohr model of hydrogen. So we've got here our hydrogen. And we see here, of course, we've got our electron. And this is going to be our orbital. Now, again, orbital, or we could call it a shell, or we could call it an energy level. All of these mean the same thing. Orbital is probably the most common that you're going to hear anyway. Now, okay, fine, that's hydrogen. Hydrogen is pretty simple. Let's do something a little bit more complicated, twice as complicated. In fact, 2 times the difficulty. We're going to do helium. I know, helium, so hard. Well, what do we got? Still got a nucleus. And in our nucleus, we're going to have 2 protons. How do we know there's 2 protons? Because if we check our periodic table, we can see that helium is the second element. First element has 1 proton, second element has 2 protons. Now the tricky part, how many neutrons do I have to put in there? Hydrogen was easy, it was 0. Very convenient. Helium, not so much. Well, how do we figure it out? We'd have to look at the atomic mass, right? How much one atom weighs. Now, we'd get that on our periodic table. And if we look that up on the periodic table, we would find that the atomic mass is going to be equal to 4.04, I think, something close to that. About 4 is the key. And if it's about 4, well, we've got 2 protons, right? So what do we do? Well, to find the number of protons, remember, we take the atomic mass and we subtract the protons, and that will tell us the number of neutrons. So we're going to take our 4 and we're going to subtract 2 from it, and that will give me 2. So there must be 2 neutrons. Hopefully that all made sense. Hopefully you were able to work through the different practice sets about this the other day, right? Atomic mass minus atomic number equals the number of neutrons. Of course, the reason for that is because the atomic mass is made by taking these 2 and adding them together. All right. So what do we have now? Well, we've got ourselves our number of protons. We have our number of neutrons. Now we need to talk about the number of electrons. Now, we hopefully remember that for the purposes of atoms, this is important, for the purposes of atoms, For atoms, the number of protons equals the number of electrons. For atoms, this, we will see in the coming lessons, is not what we're only going to be dealing with. We're going to be dealing with something else, something called an ion. But we'll get to that later. So we have ourselves our protons and our neutrons. So now we just have to put them in orbitals. Well, we've only got 2 electrons still. So the orbital diagram, the orbital structure is going to be very simple. We're going to have 1 electron there, and I'm going to put 1 on the opposite side. I don't have to. I could have put it somewhere else, but I wanted to put it there. There we go. We got ourselves in orbitals. Once again, we can clearly see there's our nucleus. This is an electron, as is this one down here, and the orbital is the dotted line. So this is a Bohr diagram. This is something that you've done before, and there are a few things to see here, right? First of all, nucleus, always have protons, neutrons. We need to be able to do this whole thing from last year, so don't make sure you can, okay? If you can't, do a little bit more practice, ask some questions. But what we're dealing with is this ability to understand the shape of things. And what we're going to find is that there are some important things, important discoveries from this particular model. Because that's what a model is for. A model is a way, it's a tool. It is a way for us to explore and to see parts of the world that we otherwise can't. Right? Atoms are too small. We couldn't really look at them. But by understanding how they behave, we can do more than we could otherwise. Well, maybe not with these two. These two are far too simple. So let's take a little further. Let's take a look at a more complicated type of atom. Let's take a look at even something just a little bit simpler. Let's go up to number 3 on our periodic table, good old lithium. So we've already had hydrogen and helium. Now we're going to take a look at lithium. And what we're going to see is that lithium follows a lot of the same patterns, but there's a subtle difference. Lithium, of course, is going to have 3 protons. How many neutrons does it have? Well, we're going to have to find out what lithium's atomic mass is in order to do that. So let's see. We would need a trusty periodic table. I have one just off screen. I come over here and I grab our trusty lithium. We stick it right here. And we reference, and it says that lithium is a 7. About a 7, 6.94, but we'll make it 7. So the atomic mass is 7. The number of protons, of course, is very easy. That's going to be 3. So we're going to do 7 minus 3, and we're going to get 4. So there must be 4 neutrons. There we go. Okay, so we have ourselves the number of neutrons now. We have our nucleus explored, explained. We have to go further because we have electrons to do. Now, this is still an atom. We haven't gotten to ions yet, whatever those are. So this is still going to have the same number of electrons as I have protons. So how many protons? I got 3, so I'm going to have 3 electrons. So 1, 2, but here's the thing. There's only 2 electrons in that shell. Then I open another shell, and I put in a 3rd electron. There are rules here. Now, these rules are not just made up. They're not arbitrary. We didn't just decide, oh, well, the first shell can only hold 2. We discovered through trial and error and a lot of experiments that the first shell only holds 2 electrons. The second shell, however, does not. The second shell holds 8 electrons. So we could map it out, right? I could say, okay, we got a nucleus, and then our first shell can hold 2 electrons max. Our second shell can hold 8 electrons max. Our third shell also holds 8 electrons max. There's a pattern to all of this. What? How can there be a pattern? Well, we're going to get to the periodic table in more detail later, but very quickly, 2, 8, 8. those look a little longer, don't they? Right? There's 8 here. 1, 2, 3, 4, 5, 6, 7, 8. There's only 2 in this row. There's 8 in those 2 rows. This next row has got 18. Patterns are good. The reason patterns are good is because they make it so we can do less work but have more information. If we can identify all the patterns on the periodic table, it will answer all our questions for us without any problem. Well, since I have a nice full valence shell here, I haven't mentioned that word yet. Since I have a nice full atom shell structure here with nothing in it, let's fill it up with some stuff, huh? Let's do another one. Let's do fluorine. I'm not going to do the middle, not this time. Let's just do the outside. Fluorine. We take a look at our periodic table and we find fluorine. It's going to take us a bit to look, but we find it. F is going to be here in number 9. Right here at the end. So number 9 means that there should be 9 electrons. Okay, well, the first shell can hold 2 electrons. We said that. So I'm going to make a little bit of space at the top and the bottom. I don't have to put it at the top and the bottom. I just am. There's our electrons. The next one is going to have 8. Okay, well, there's a couple ways we could do this. 1, 2, 3, 4. 5, 6, 7, 8. But wait a second. How many electrons can we have in total? 9. Oh. Well, we're not going to have enough to fully fill in 8, are we? Right? We've already done 6. We can only put 3 more, right? Because we are a total of 9, and we've already put in 6. 1, 2, 3, 4, 5, 6. So we can only put in 3 more. Now, often students will want to do something like this. 1, 2, 3. That's not accurate, I'm afraid. If there's more than 4 electrons, what you're supposed to do is you're supposed to start pairing them up. They team up. It's kind of like they can't afford to rent an apartment on their own, so they share the rent. They get 2 roommates. So instead of separating them out like this in the spaces, what we're going to do is put them next to the guys that are already there. Well, we don't need that last shell, right? Because we're already full. We've already got as many as we can because we're out. So there we go. Now, why is it useful that we do it like this with the pairing? Well, first of all, I think you can see, or I hope you can see, that it's much quicker to pull out information, right? We look at that and go, oh, 2, 2, 2. I can see it much faster. I don't have to count around the circle. It also happens to match reality a little better, which is always nice with our models. You'll see here, of course, that there's an electron by itself over here. This poor guy's alone, very lonely. Don't worry, we'll figure out how to fix that once we get to ions. Now, this particular situation and this particular situation, in fact, both have something interesting going on because both of these have got 2 different layers, 2 different shells. And the outside shell has a name, the valence shell. Is the outside shell, or the outermost shell. The idea behind the valence is that it is the shell on the outside. Now, why in the world is the word valence used to describe a shell on the outside? Quite simply put, it's a very important thing in chemistry. Practically all chemistry is going to be dealing with the valence in one form or another. It is of vital importance that you know what the valence is. And like most words, when you first learn it, it's like, I don't know what that means. But as you learn it, you automatically know what the definition is as well, right? If I tell you something is wet, I don't have to explain what wet means. You know what it is. If I tell you something's a valence, right now you're like, I don't know what that is, but you will, because we're going to be using it a lot, okay? All right, that's the basic of a Bohr diagram. A little bit of a refresher, a little bit of review. Over the next couple pages in your notes, you're going to find that you've got some practice to try, okay? So take a look through those. Fill them out. Do the best you can. If you have any questions, I will, of course, be helping you. Once you do that, we're going to be taking a look in more detail at the periodic table. As I mentioned, if you know how to read this table, you actually have almost all the answers to this class given to you on a test. But we've done enough today. I will see you guys next time.